Python kind of session you could actually take to review some of the key kind of like, commands or the coding lines that you probably forgot where you haven't used it for a while. So if you click this and open this, it will actually give you a kind of like I wouldn't say like a 360-degree or the full or comprehensive introduction of the Python, but it will just give you most of the libraries or most of the commands we're going to use when we actually taking off this kind of course by learning more lectures in the future. So it tells you what is Python, why do we use Python, and then more important later, it tells you how do we actually use different kind of like a list here. How do we slice in the list, right? How do we actually use a tuple or dictionary, or what is a class, what is a function, and what kind of library can we use, like a NumPy? What is NumPy, and what NumPy can be used for? It's more like a matrix multiplication or matrix manipulation, to be honest. So if you have no kind of Python, foundations, I strongly recommend you to actually go through these slides. Or if you forgot about most of the Python kind of like libraries or commands, just go through these slides first. It will help you dramatically to get like a more kind of general sense of what kind of language we're using for this course. Okay, all right. So today we are gonna actually take off and learn the first kind of chapter here, which is called Introduction and Word Vectors. Okay, so this chapter will just give you kind of like a really brief introduction into natural language processing. Like, what is natural language processing? Why should we learn it? And what can natural NLP use it for? And after that, we're gonna actually talk about how do we actually transform the words into numbers so that we can put into the model. We can use those kind of words to construct like a bigger models. And what kind of models can we use with all this kind of like number represented text? Okay, so first part is natural language processing. So just like I mentioned in our previous conversation, natural language processing is really, really important and also kind of like popular fields that's kind of embedded with deep learning. So basically, it focuses not actually on the numbers, it focuses more on the text, on the words, language you use every day, and we transform these kind of texts into numbers, and we try to use those kind of languages to make some prediction or classification. So like I mentioned before, there's so many different applications we can use with NLP, spelling, kind of checking, keyword search, Google engine search, question answering, conference, semantic analysis, so on and so forth. So we already actually talked about this, so I'll just skip that part. So next part is, since suppose, we have a lot of words. We talk about words every day. We have a lot of words, and we have data of a lot of words, like one person just said every day. How do we actually transform those kind of words into numbers? Because, the model doesn't take text. It doesn't take like 1, 2, 3, 4, ONE or TWO, those kind of, words. So how do we actually represent the words? How do we actually transform the words into numbers? That's like the first step we should actually definitely learn before we actually head into the model part. So there's actually a lot of methodologies you can use with the words representation. So the first one is called word vectors. So this is really simple, actually. For example, we have all those different kind of words over there. So suppose we actually start from this word. We have, what is that? Work, and at, until the last word in the corporate, which is zebra. So suppose we have all those words. How can we actually represent those kind of words? So first methodology you can use is actually one-hot encoding, just like we had before. The first word here, we'll just give it a 1. And the other words, we'll just give it a 0. The second word here, we'll just give it a 1. And other words will be 0. Third words, 1, other 0. The last word here, 1, other kind of words, 0. So That's one way to do this. That's actually the one way to actually represent the words. But what kind of disadvantage can you guys come up with this kind of representation? Like, when do we use it? When do you think we can use it? Like, under what kind of circumstances we probably shouldn't use this kind of word representation? Start from the first one to the last one, and we just represent each word with a 1, and the other word will be 0. Okay, for example, suppose, I'm gonna write here. Suppose we have, let's see, those words. And I try to represent all the words using this methodology. What's the dimension of these words? Words matrix, actually. These were the word matrix. Anyone? We have 1 million words here, and we try to represent the words using this methodology. And what kind of dimension do we have for the word vectors?
Do they have to be unique? I mean,
it doesn't have to be unique. It can be, but it doesn't have to be. Yes.
So if it's unique, you're going to have the same a million times 1 matrix.
Okay. For example, think about the first word is A. Think about the first word here is A. And what's the dimension of this first vector here?
Yes, a million or whatever is the number of words you have, right?
Exactly. 1
up to that
times 1 million, right? So that's actually it's 1 million times 1. Sorry, it's 1 million times 1, right? 1 million rows times one column here, right? What if I just concate all the words into one matrix? Let's just put all the words into one matrix. It would be this, right? Is that right? And the problem with this part, just make sure you guys get it, this part. Is that correct? We have 1 million words. If we put all the words using 1,000 encoding, we could have 1 million times 1 million dimension for the word matrix. Okay.
Yes.
So what's the problem with this?
Too big.
Go ahead.
There are just 26 letters. We don't need 1 million, right?
Exactly. There's a lot of zeros, right? There are a lot of words we don't actually use over there. So for each vector, we only have 1 over there, right? So it's so the first kind of problem is too sparse. It's just too sparse, too many zeros. We don't need those zeros. What's the second problem? What's a more kind of direct problem you can come up with this kind of matrix here?
I can think of storage.
It's a very huge
exactly.
matrix.
Go ahead.
Very huge matrix. It's difficult to solve.
So the dimensionality occurs, right? So it could explode. So we only have 1 million word here, but actually in a dictionary, it could be 1 billion, 2 billion, 4 billion, even 10 billion words over there. If we try to represent every single word using a word matrix, right, it will be a huge matrix, and it will cost huge memories to actually calculate it, or put into a model. It's probably going to take years or even days to, find the final result, right? So the first kind of problem is too sparse. We don't actually need all those kind of words here. We probably don't use a 0. We just need 1. Second is the dimensionality. Right? So we have 2 problems. So next, we have to think about a way, we have to think about a solution to solve the 2 problems. How can we just get a clean, organized word matrix with not too many zeros, but also the dimensionality is not a concern for us? So there's one basic methodology we can use, which is called SVD, singular value decomposition. Okay, it's called a singular value decomposition. By the way, if you don't know, what SVD is, you can check those here. You can check the more details here. I'm not going to go through this, but I'm just going to give you kind of like a really brief, like kind of like introduction or explanation of what SVD represents. So basically, SVD said you can actually suppose you have the word matrix. Suppose this is the word matrix we have. Suppose we have just like before, we have the 1 million times 1 million word matrix. And SVD tells you, you can actually split or kind of decompose the word matrix into 3 matrices here, like right here. You can actually split it into this one, that one, and this one, 3 matrices here. And this matrix here is called singular matrix. So it only has values on the diagonal kind of line here and 0 everywhere else. And this matrix is actually, I would say it's like a singular, it's actually called eigenvector matrix. This is eigenvalue or singular value matrix. This is another eigenvector matrix. So basically, SVD is a way to decompose the matrix so that you can extract the key words. That is, you don't have to use other words. This matrix decomposition can tell you what kind of words you can actually extract or what the most important words you can use. So for example, suppose we have, 1, 2, 3, 4, 5, 6, 7. I like flying. We have 3 sentences. I like NLP and I like deep learning. We have other words here. Then we have a word matrix here, right? So what can we do is we can actually break or decompose the word matrix here into 3 kind of like a matrix. And that's the first step. Second step is this middle matrix here actually tells us, gives us the information on which word is more important or which group of words are the most important ones. So the sigma 1, sigma 2 values actually tells us the importance of each word. So if you look at sigma 1 here, it represents the first word, the importance of the first word. And this corresponds to the first column of the V matrix here. So the first column of the V matrix is actually the first word. Okay, so first word, second word, first word, second word, first word, second word. So second step, okay, next step. What if I just want to keep 4 words? So what I do here is I rank all the sigma here. Or suppose sigma 1 is 0, sigma 2 is 1, then I put sigma 2 on top. So that means, sigma 2 is more important than sigma 1. If I have sigma 3, which is 4, then I put it on the top. So you kind of rank descendingly from the top to the end. Then suppose you just want to keep 4 words, then you just truncate the matrix with 4 words left on the top. So suppose we just select sigma 1, 2, 3, 4. That means we're going to stop here with a U4. That means all the left words doesn't matter. We just care about the first 4 words. And those first 4 words are the most important ones. Okay. So in that way, we kind of truncate the matrix, we reduce the dimension, but also we don't have a lot of zeros anymore. We're left with a smaller matrix, with not 1 anymore. Actually, after this kind of SVD decomposition, we are left with non-zero values, which I'm going to show you in assignment later. Okay, so that's SVD. That's how we can solve those kind of problems right here. Any question with this part?
I was wondering, we're talking about words. How do you determine what?
Can you speak louder?
Is it better now?
Yeah, a little bit better. Yeah.
Okay. Yeah. So I was just wondering, when you were talking about the importance of words, so the values on the diagonal values in the matrix middle, how do you determine what kind of words are more important than others?
Oh, okay. Basically, just like I said here, sigma 1, 2, 3, 4 is a number.
Yes.
Basically, this number here, suppose this sigma 1 is 0.4.
Yes.
It means, this kind of like a words explains 40% of the total variance of all the words.
Oh, so it's like, is it like R squared type of a?
It's actually not a type R square. It's an eigenvalue. You think about its contribution to the entire matrix. So think about the information gain. So suppose we have this kind of, like a word matrix here. And I just want to know how much contribution does each word contribute to the whole sentence.
Mhm.
So basically, that's what what this eigenvalue tells you. If it is 40%, that means it's a little bit important, but not that important. But here, if it's 90%, then I know this is like probably the most frequent words I'm going to use. That's super important. I should keep that.
Okay, thank you.
Yeah. Okay.
So
yeah, go ahead.
Sorry, your rank is SVD as the frequency of the word. Is that correct?
Oh, the sigma here is not a frequency of the word here. I would say here, inside here is a frequency, which I'm going to talk about now, actually.
Okay.
Yeah, so very good question, actually. So Empathy just gave us a very good question. Like, what kind of like matrix are we going to have before we do the SVD? So this is actually the matrix we're going to have. For example, I have the 3 sentences here. So this is called a window-based co-occurrence kind of matrix here. You can also do other kind of matrix here, but this is like the most commonly used. So I'm going to just give you an example here. Okay. So first of all, you can do Word document matrix. For example, you can think about what we just had here. Think about this. Think about this is the first document. I enjoy flying. That's the first file. This is the second document. This is the third document here. Okay. So if you think about this is actually 3 documents here. So what you have is I'm going to make each row as a document. And I'm going to make each kind of word as a column. So it's going to be like, let's see if I can draw this. So, draw. Okay. Here we go. There you go. So think about it, it's a matrix. It's going to be like this. So this is doc 1. So that's our first row here. And doc 2. And doc 3. And this is word 1. And this is word 2. Word 3, 4, 5, 6. So unique words, like they're not repeated here. So what you put here is how many times does this word show up in document 1? How many times does the first word show up in document 2? How many times does the word show up in document 3? So on and so forth. So that's called, actually, I'm going to go back here. That is called Word document matrix. Okay, Word document matrix. Basically, it's a number of times that each word show up in every single document over there. Okay, so that's one way to do this. But again, this kind of like solve the problem we had previously, which is a word-to-word kind of like a representation, not a Word document matrix. So previously, just like this one here. Just like this one here. This kind of solve that problem. But what if we have a lot of documents, right? If we have a lot of documents, it's still kind of like a big problem to us. So another kind of way to represent the word vectors is called window-based, like a word vector representation, which is this one here.
谁是这个 meeting 的 host？ 还有同学没有进来。
I think it's Xiaolei.
Lindsay is saying that she's waiting for your admit.
I just admitted.
Okay.
Oh, okay.
Sorry to interrupt.
It's okay. It's okay. Okay. Any other questions? Okay. So that's one way to do this. That's one way to actually solve the previous problem. You can do SVD, right? But before SVD, like I said, we have to get a matrix. You can do Word document matrix. But now the better way to do this is called a window-based co-occurrence matrix. So what does window-based co-occurrence matrix mean? Basically, you have a long sentence. Suppose I'm going to do this way here. So I'm going to just type a sentence. So type it right here. CADASA is the most important organization in this whole world. Okay, suppose this is like, the sentence I actually just typed right here. Again, I don't want to use a word-to-word kind of representation. I don't want to use a Word document representation. So what can I do? what if I just, cut the sentence into several different windows? Suppose from Cadassa is the most important. Suppose I use a 4-word window. This is the first window. That's the second window. That's the third window, right? I can kind of repeat it. I can repeat the window. They count the times every single word show up in each window. Okay, so again, I'm going to repeat this. Break the sentence into several different windows. Count the times each word show up in each window. So that is called a word-based core occurrence matrix. Word-based, like a window-based core occurrence matrix right here. So it actually gives you an example here. Suppose I have the 3 kind of like a sentence here. Okay, you can put the whole sentence as a window, or you can actually break into several different windows. But here, actually use the whole sentence as a window. So I enjoy flying. I like deep learning. I like NLP here. So what I do is, I put all the words right here. I'll put all the words right here on the column. I also put all the words here as a column here, as a row here. So I count the number of the times that each word follow the previous word. Okay, I count the number of times each word follow previous word. So basically, that's a word, window. So for example, I never followed I, but I followed like twice. So that is actually a window. So that's a 1-word window. So basically, I'm just looking at these kind of 2 words here. Next part is I. Does I followed by enjoy? Yes, once right here. Does I followed by deep learning and NLP? No. Okay, so it's gonna be like a symmetric here. So like and like, right? Enjoy, and here enjoy never followed by I, so it's 0. So it actually is 0 here. So as you can see here, is actually a 1-word window that you actually count how many times this word going to show around that word. Okay, so this is called a window based. Also, you can do like 2 window based. For example, I just want to count like how many times like NLP will show up after I. Then here it will become I like NLP. It will show up like once. Okay, so this is just a 1-word window, but you can do multi, kind of like a word window there. So that's one way to represent the word. So in this way here, it's going to actually break the sentence into small pieces. So it reduces the dimension like dramatically. Also, it gives you some kind of sense of the window. Because sometimes when you talk about something, it has to be in the context to make some sense here. If I just look at the whole sentence, it probably doesn't make any sense. But if I just look into specific windows, like is actually a verb, NLP is a noun. So verb followed by noun, yeah, it totally makes sense. Okay, so that's basically the intuition behind the windows here. So this is actually the most common used like a methodology to represent words those days for an NLP. Any question about this part? Nope. Okay. So that's how we represent a word and how we reduce the dimension and using SVG.
Could you please go back to the matrix?
Okay, sure. This one here.
Yeah, from the second row, why like could be followed by I, the second row?
Okay, so it's not like followed by I, it's like showed up around I twice. So think about this way here. I'm gonna actually draw this. So think about this is a window. This is a window, okay? And this is the center word. That's a context word. How many times does like showed up around the center word? Twice. Just doesn't care. We don't care about the order. We don't care about it's followed or lagged or lead. We just care about does that show up around this inside this kind of window here.
Okay,
If I insert a don't in between the two.
If I insert don't here, yeah, that means this number here will be 0. This number here will be 0, and don't will be 1, 1.
Okay, so it can be before or after, but it can't have you can't skip.
Yeah, so basically you can like break the sentence into a small window, like a 2-word window. Okay, Like, so, okay, let's do this way. So think about this. First window, if I just use the 2-word window here, that's the first window, right? I enjoy, right? What's the second window?
Enjoy flying.
Enjoy flying, yes. So now let's go back to our first window. How many times does enjoy happen in the first window? Once. How many times does flying happen in the enjoy flying window? One, exactly. So don't think about the order. Don't think about it's followed or not. Think about whether it's in the window or not.
Okay, and you specify 2 words in one window, but you can also specify 3 words.
Exactly, yes. You can specify 3 words, 4 words, 5 different words. Yeah, in that way, it will have a more kind of number. It's definitely going to be some number greater than 1 then, yeah.
Okay, cool, thanks.
Yeah, so that's a good question. What's a window size should be? It actually, there's no standard answer for this. It totally depends on your kind of preference and depends on how long the sentence is going to be. So usually we'll actually start from 5. So after that, we'll use 5, 15, or 10. So usually just 3 different kind of standard we use for this. So we barely use like a 2-word. Okay, 2 words is too limited. We only have 2 words in a window and doesn't tell us too much. Does that make sense to you guys? So this is just an extreme case. We barely use like 2 words. Most of the time, we actually just use like 4 or 5 different kind of like words around the window so that we can have more words that actually make sense in this case. Okay. So again, just remember this. This is actually quite kind of like a popular way to represent a word. Instead of just looking at the whole matrix, we actually look at each window, which actually makes more sense and actually saves more time here. Okay. So that's this part. Skip that. So here is like a matrix, like it's actually a specific example I use, like how SVD gonna apply to the co-recurrence matrix. If you're interested, you can actually take a look here. It tells us all the transformation kind of process. So, you know, in that way, you can actually tell like how SVD gonna help us to truncate a word. Okay, so that's basically the word representation. Next part is called iteration-based methodology. So this is like a one type, so this is before we actually use the AND model. And next part, like starting from this point on, I'm gonna tell you what kind of model can we use to make a prediction or classification. Like Chen Qian just said, like, you know, the regular basic, like a simple expression, what kind of model in that part we can use. So as you can see here, those kind of like word matrix here actually use one common kind of like regular kind of common thing here is occurrence. So it's the number of times that each word show up in a window or in the document. So there's a problem with this. So the occurrence, yes, it tells us some kind of like thing. It tells us like, you know, how frequent words can be used. And the more frequent the words going to be used, maybe that's more important, right? But what if I just want to have the meaning? I just have the meaning of the word. I just want to know, you know, what does like mean? Like it can be, I like you, or it can be, you know, things like, right? So it can use it for different ways. But if you just count how many times like showed up in each window, it's not going to tell you which like it is, right? Does that make sense? So in that way, this is actually not like a comprehensive model we can use. So this type of word kind of like a representation kind of like methodology is called like occurrence or counting-based word representation. So next, starting the model here, we're gonna, you know, kind of like get starting from a different perspective and move to the context or the semantic meaning of the words a little bit more than just like the counts. So the most basic model, every single time when you talk about an NLP, this is definitely the model you can never get around. So it's called word to vec. Okay, it's kind of word to vec. Basically, you're kind of converting a word to vectors and use vectors as a model here. So what is a word to vec? So this is actually a pretty kind of new methodology, which is invented by Mikolov like in 2013. So the basic idea here is first, we just get large corpus. We just get a large corpus with as many words as we can. Second each kind of word is represented as a vector. Okay, each kind of word is represented as a vector. So what does that mean? For example, we have the word chain here. So I'm going to transform that into a vector, and the vector could be this vector means chain. Okay, this vector means chain. Basically, I just kind of encode it into a vector, just transform that into a vector. How do I actually, transform it into a vector? It doesn't matter. Sometimes you can use like a byte-wise. You can just use like, each kind of like you can just use a MOS, or you can use like other kind of methodology to encode this letter. That's not the focus of the course, but just remember this. We can actually convert each kind of word into a vector. So in this way, the vector would be 1 times 5. The dimension will be 1 times 5. Okay, so that's the second step. Next step, for each position in the text, for each position in the sentence, we're going to have a center word and we're going to have an outside word. For example, here, problems turning into banking crisis as. So the center word here will be into. Problems turning banking crisis as will be the context word. Okay, it will be the context word. But it also depends on how large the window size is. If the window size is 2, that means only those 4 words are the context word, and this word is the center word. Okay, is center word. So basically, you have all the vectors, and you're going to name one of the vectors as the center word, and other words will be the context word. Okay. So next part is we're going to use the similarity of the word vectors for the center word and the context word. We're going to calculate the similarity between those words. And then use that, we're going to calculate the possibility of the context word given the center word. So this model basically tells you a way to predict the surrounding word, the context word using the center word. That is, you give me into, I'll just predict the next word will be banking. The previous word will be turning. And the word before turning is a problem. Okay. So basically, you give me this, I predict all 4 words here. So that's one way to do the word vector. Or you can do the reverse. That is, I give you all the 4 words here, problem turning, banking crisis. You tell me what's the center word. Okay, so that's word to vec. Okay, so word to vec basically is like try to transform the word into numbers, into the vectors, then break the vectors into center word and a context word, and use one of them as input and try to predict another as output. Okay. So that's a basic idea of the word to vec. Does that make sense to you guys? Okay. So since we have the window size 2, for example, that means we don't stop here. We kind of like moving around every single time by 1 word. So we slice 1 word forward, then the next part would be this is the center word. That's a context word. Okay, so you will keep doing that until you finish using all the words out in the corpus or in the text over there. Okay. So how do we actually establish a model? The model will be, or the possibility here, like the possibility given the center word, what's the possibility of this word to show up given this word? That can be established as this. Okay, can be established like this here. Okay, so basically this is the center word. That's a context word. So what we try to do is we try to maximum the likelihood that given the center word, the context word will show up around the center word. Okay, this is called maximum likelihood, like a methodology. We actually talked about this before using logistic regression. Okay, so how do we actually maximize this? So we take the log, so it will just transform all the multiplication into the summation. Then this is the final log, maximum log likelihood function. We're going to use it as a loss function. So this is the cost function. Okay, this is the cost function we're going to use for the model. But now we only know that we just want to maximize the possibility. But what does the possibility is? What is the possibility? What does that represent? So A actually can be represented in this way. Okay, so well, the possibility has two parts. On the numerator, it's actually the exponential of the context word vector times the center word vector. And the bottom part is a summation of all the combinations of the center word and the context word. Okay, so basically on the top is just a specific, for example, just this part I'll put on the top, and every other combination will be at the bottom. So the next part will be just like this part will be on the numerator, and every single part other than that will be on the numerator, denominator over there. Okay, so that's how we actually represent the similarity or the possibility of the context word giving the center word over there. Okay, but why do we actually use the multiplication of the two, right? Why do we use the multiplication of the two to actually represent the correlation or the possibility? So this is actually a concept called cosine similarity. Cosine similarity. You can think about each word as a vector. So we talked about previously, we actually transform every single word as a vector. So suppose this is a vector. Okay, this is one word. This is called word one. This is another vector. Okay. Think about those two vectors. Think about them actually, taking different directions, like two different directions here, and their angle could be, suppose this is just, suppose the angle here is 90 degrees. Okay. If that's the case, what's going to happen if the two vectors actually driving into different two directions? It's going to be canceled away, right? Or it could be like this. It could be not cancel away. Sorry, it could be like this. It could generate a third vector in the middle, right? But what if I have this example? Think about another example here. So for example, think about this. That's the first word vector. That's the second word vector. If those two word vectors are driving in the same direction, in total, the vector will become even bigger. Okay, so basically the cosine similarity tells us if the two word vectors are pretty similar to each other, then their multiplication will just give us a bigger value, which represents the similarity is bigger between the two words. For example, suppose the first word is 3, second word is also 3. If you multiply 3 by 3, that's the same word, right? It will be 9. But if the first word is 1, the second word is 3. If you multiply 1 by 3, it will only give you 3. So now the similarity decreases. So that's why we actually use the multiplication here to represent the similarity. Okay, hope that makes sense to you guys. So that's actually called a cosine similarity. Okay, so I'll skip that part. So that's how we actually construct the model here. Clean up this. So now we know that the P is actually this function here, right? It's actually this function here. That's actually replace the P into the logical function we had previously. Okay, so in that way, we have a new kind of logical function. So how do we actually calculate the parameters? How do we actually calculate the weights of each vectors here? So think about how do we actually calculate this parameter and that parameter, the center word and the context word? How do we actually calculate the predicted like a word over there? So the way to do that is basically you make the first order derivative with respect to the center word and the context word separately. At the end, I'm going to skip those kind of whole mathematical derivation. At the end, if you just make it a prediction or make it the first derivative with respect to the center word, it's going to give you this final equation here, which is U0, which is observed representation of the context word. So just like we said before, O here represent a context word, C here represent a word. So that's a center word, that's a context word. So it will be observe kind of context word minus the summation of the possibility given the center word times the context word. So this is actually the mean or expectation, or expectation is actually more precise. Expectation of the context word or conditional expectation of the context word given the center word. Or you can think about this is the prediction of the context word using the center word. So basically what's this? That's the difference between the real context word you have and your predicted context word. So this is actually the residual. So what we do here is we try to minimize this as small as possible. We try to minimize the difference between the reality of our prediction. And that totally makes sense. So that's why we make the first order derivative right here. And we try to make that equal to 0. Okay. So yeah, that's basically how we actually use word-to-vec optimization, like a word-to-vec model here. But how do we actually, start the whole process? We can actually just make the first order derivative with respect to every single context word or every single, center word. There's a lot of them, right? You cannot just make the first derivation with respect to word vectors, which is like 1 times 5 or 5 times 6, right? It's going to cost you a lot of kind of memories over there. So what we do here is that we use gradient descent to actually find the local minimum, to find the best context word or best center word over there, or our best prediction. So basically, gradient descent is just like we had before. We started with initialize, like, center word or context word. So previously, just like we had before, I'm probably gonna initialize with this part. I'm saying, oh, this is center word, that's a context word. I initialize those count as the beginning point or the starting point of the center word and the context word. Then I make the first order derivative of the loss function, which is here, with respect to all the words over there, center word and context word, then update it just like before, right? So I keep this kind of loop and I keep updating until I find the local minimum. So that's basically how we actually find the local minimum or optimize the model using gradient descent over there. Okay. So yes, that's basically everything about the first chapter. Any question here?
Hey, Daniel, can you go back to the last point you just mentioned, that the
Yes.
gradient descent method?
Yeah.
Can you repeat that section? Thank you.
So basically, what do you do here? So I only show you here, which is the first order derivative with respect to the center word, right? But that's only one of the vectors you try to find. You also need to try to find this, right? So you have to make this kind of first order derivative with respect to this as well. So basically, you're doing 2 derivatives at the same time. Okay. So that is the first order derivative is actually this. It's actually this here. Okay. So basically, what we do here is we initialize like a center vector and a context word vector, and we subtract a learning rate times the derivative from that, and we get a new kind of like the parameters over there. So again, this is the learning rate, and this is the first order derivative. So okay, I'm going to explain a little bit here. Why do we need those 2 for the updation? So think about the log likelihood function. Think about this log likelihood function as this. Let's see what I can draw here. Okay, think about the log likelihood function like this. And each of the circle here is actually a level of a loss. So each of the circle here is, I would say here, let's just type it here. Each of the circle here is J theta. Okay, each circle here is G theta. Okay, so what do we do here is like, we try to find the minimum G theta. We're trying to start, suppose I initiate a point here, starting from here. I just want to find a path that actually gonna lead me down to the bottom. Lead me down to the bottom over there, okay? I just wanna find a path that actually starting from here is gonna lead me here, okay? So how do I do that? First of all, I need the direction. I need the loss function tells me which direction should I go? Should I go that direction, this direction, or that direction, right? So what the first order derivative do is it tells you which direction you should go. Okay, so that's why we actually do this first order derivative first. Second is, the second kind of point is, how much should I go? You know, should I actually just go, should I just go from here? Should I just go this little bit? Or should I go that huge step? So that's why we just add another kind of like parameter here, which is alpha. That's a learning rate. That tells me how much more should I move towards the local minimum over there. Okay, so basically you start here from here with the theta, and you move a little bit, then you get a new theta, then you keep moving until at the end you reach a local minimum here. Okay, so I forgot to mention part. So we try to maximize the likelihood. So if we just try to transform that into minimum like a problem, we just need to add a negative number in front of it, so that we try to minimize this, and that's the same as maximizing loss function over there. Okay, does that answer your question?
Yes, thank you.
Yeah.
So, hey, Daniel.
Okay.
So for the likelihood, are we only consider the distances between each words, or are we also consider the actual vector values?
Oh, we care about the actual vector value. We don't actually consider the distance. So basically, we take each single word, we transform that into a vector. And after the first order derivative, what we get is still the vector. We try to get the real vector as close, or the predicted vector, which is as close as the real vector.
So how we encoding the words will affect our likelihood calculations, right?
So this one here, oh, you don't have to. There's a library. You can just put a library. You can just put all the words into a library. It will actually do all this kind of thing for you.
Okay.
Yeah. So what do you do? What you need to do is actually first construct the word vectors. That's it. So after you construct the word vectors, you put all the word vectors into like this. Basically, you just need to construct all the word vectors here, and you tell the model what is the center word, what is the context word. Then the model will just do everything for you.
Okay, got it. Thank you.
Yeah. Yeah, so don't worry about this kind of mathematical expression if you don't understand it. It just like it tells you how the model gonna work. But there's a library which is called Word2Vec in Python and also in GenSim. It's gonna actually process everything here for you. Okay. So last part, I just want to show you guys a little bit about like an interesting application I mentioned previously, like the GenSim library here. Let me just clean everything. Bit. Okay. Okay. So should do this one here. If you're interested, you can just try this yourself, but I'm not gonna actually run this kind of library here because it's gonna take a lot of time. So basically, this is like a GenSim, like a word vector visualization. Okay, so what do we do here? Basically, what do we do is we just import, which is called, I'm going to tell you next lecture probably, if possible. It's called Glove2Vec. Glove2Vec, kind of like a library. This library is a combination of the Word2Vec and also the content-based library, or the model we talked about previously. So in this kind of library, it has several important functions. And one of the most important function is it can tell you the similar word. It can tell you the synonym of a word. For example, I use most similar function of the model, and I just put the Obama inside this function. So guess what? It gives you Obama Barack, which is about 93%, kind of correlation between this word and that word. It gives you Bush, 93% as well, Clinton, right? So that's one kind of example. And also you can put a banana into this kind of like a library or the function here. It's gonna give you coconut, mango, and also the correlation here. And if you just want to find some kind of like, not kind of similar word, but non-similar word, you can just put a negative over here. And it's going to give you other word which is barely kind of correlated with banana. Okay, so basically those words, I don't even know what that is, but these are not even kind of close to banana at all. Okay, and another function is you can make like correlation rules. You can actually create your own correlation rules for the word so that it can predict a word for you. For example, suppose after the two words, woman and king, and I have one negative. So basically, this is the two inputs over there. Another input is a man. So what I do here is I tell the system I have the word woman, I have the word king. The next part is I'm going to subtract the man from the king. I'm going to subtract the meaning of the man from the king and add that on top of the woman. Okay, so add that on top of the woman. If I just do that, I would just get a word which is, it doesn't give me right here. It should somehow.
It's queen.
I think it's a queen. Yeah, it doesn't give me that example here. So it would just give you a word queen. For example, if you just do, so this actually happens, this is like the same kind of function here as well. So you can use another analogy with the same kind of function we just talked about previously. So this is another function, which is, those two are the same, okay? So if you put Japan, Japanese, and you put Australia, it will give you a word Australian, okay? If you put a man, king, and a woman, it should give you a queen. Or if you give Australia beer and France, it will just give you a champagne. Okay, so it's kind of correlation you created between the first two words, and then the model going to predict the next correlation given this word you have, the third word. Okay, so that's a pretty kind of interesting, I would say pretty interesting kind of like model you can use here with the word-to-vec model we just created. So basically this is after we finish the word-to-vec model, then everything is right here. You can actually use all the functions right here. Okay. Yeah, I guess that's everything for today. Any other question with respect to
this
lecture?
process monitoring?
Sorry, say it again.
Can this lab or function process monitoring?
Mandarin? Oh no, I don't think so. This is created by Michael Anderson, who is actually the lecturer, or who is actually the associate professor. I think he's a professor of this course. And he actually invented this library, but I think most 100% is just English. It's not for Mandarin. Yeah.
Or do you know, is there any library can process Mandarin?
To be honest, no, I don't know actually. I think probably back in China we have some kind of library or self-created library over there. But most of this kind of like NLP library is basically focused on the European language, like Germany or English or French. Yeah, that's a good question. I haven't seen any kind of library using Mandarin yet, but it should be some, but it's not here in this course. Yeah.
Yeah, I think there's a library in Python called PyTesseract. Tesseract, it can process Mandarin, but the accuracy is a little bit lower than it process English.
I think Lynn's just shared something here, but Chinese like a natural language processing and speech processing. Okay. Okay, yeah, so at least we got something here. But is this for this course here? Oh no, it's actually by the students over there. Oh, I see. Okay, yeah, it's actually not about this course. It's actually a group of students who actually published their paper in semester. Yeah. Feel free to check out this kind of like, I'll put this into the link as well. Okay, if you are interested, you can check out this. Yeah. Thanks, Lynn.
So the window is just for reduce the dimension and find the keyword.
Reduce the dimension, that's the first point. Second is the word makes sense inside the window, right? So when you talk about a word, you cannot just talk about a single word. If you just put a single word here, it doesn't mean anything. If you put a word into a window, it has a context. So in the context, the word has some meaning, right? If you just I just give you a word like, I don't know, I just give you a word like. What does like mean? It doesn't have any context. What kind of meaning am I supposed to guess? But if I put the like into the window that I like food, then suddenly I know, oh, like means like, enjoy, right? So that's another kind of intuition why we use a window. Yeah.
Okay, I see.
Any other questions right here? Okay, if you're interested in this, please just like I'm gonna do another kind of like maybe some kind of vote or some kind of questionnaire in the WeChat group and count how many people are going to join us in the group. And if you're interested in this, then you should actually head into the first assignment today. You should actually start, working on the first assignment today and thinking about how you can get some kind of solution to that assignment here. So the assignment here, if you click that, it will just download all the assignment with all the data and everything you needed here. So that's definitely assignment 2 here. So assignment 1 should be here. Okay. So if you're interested, you probably should start like kicking off this course by doing the first assignment here. And in the first assignment, it basically tells you, give you everything you need, like images or some kind of like, it's kind of like a notebook that already have all the questions. You just need to type your own words to finish the answer. It's more like an interview question over there. Okay. All right. Any other questions here?
Hi, it's not really about today's, like the topics that we covered today. I'm just wondering that I read this somewhere that NLP is a field that has developed a lot since 2018. It had this like breakthrough around that time. So I was wondering, are we going to cover things like BERT or like transformer, the newer things that got out this
Definitely. See, definitely. We have machine translation here. Which I think is going to happen chapters later. Yeah, we're gonna cover that as well for sure. For example, we have what do we have? RNN, recursive neural network, right? We have machine translation, right? Which is like a Google Translation you saw previously, and we're gonna have a lot of other more like transformer and self-attention, right? And reference language conference. Yeah, so we're gonna have a lot of those covered in this course for sure. Because this course actually started, we actually just looked into the course in 2019. So it's actually after it's actually most kind of like a recent course we had. And I actually just released like the 2020 version here, which is right here. So it basically covers the most cutting edge kind of like the technologies we actually probably gonna see in the next few years. Yeah.
Okay, thank you.
No problem. Any other questions? 好，就是我们今天的全部内容。如果你感兴趣的话，我们